Hey YouTubers, Flat Earth believers, globers, subscribers of my channel. Thanks for visiting this YouTube video again. I hope you like it. Have fun.
Hello Flat Earth researchers, debaters and debunkers. This is going to be a quick and simple demonstration of perspective, one that's pretty obvious but one that has to be pointed out because so many people are still denying that perspective is a thing and are really trying hard not to get it. So just showing here that from the side, this external reference frame of these bottles on the table, we can see very clearly that they are all the same height. Yeah. Now you can imagine that these bottles are, say, electricity pylons going across Lake Pontchartrain, if you like, or you can imagine that the tops of the bottles represent a sun traveling above the flat Earth at a consistent height. Yeah. We have this external reference frame, which with the ball Earth we have to imagine anyway, so just apply some more imagination to this little scenario, but take note of the two observations that have to be made here if you want to prove curvature. Okay, we see that they're all the same height, yeah, on this flat, smooth surface. A man-made surface, which you will not find in nature. Of course, roads and lakes and sea is rugged in its nature and it's affected by temperature differences, etc. So there are many other factors involved in these observations, but what we're looking at here is perspective and how we should be making scientific observations if we want to prove curvature. Yeah? So we know that these are all the same height, but of course when we come over here we see this dramatic change in perspective. Yeah? They all appear to shrink towards the end of the row there. Yeah? So if I just put the camera down here, we can make a few more observations as well. Yeah, people talk about angular size, and yes, there are angles. There is an angle at which these bottles appear to be descending towards the horizon. There is also an angle at which the flat surface appears to be rising up to eye level. Yeah, it might not be precisely eye level because the table's not very long and we have a wall in the way, but you can see that I have to raise my hand an inch or so to bring it in line with the end of the flat table. Yeah, so this shows us that the flat surface appears to rise to eye level due to perspective. Yeah, just as the bottles appear to get shorter and to converge at the horizon due to perspective. Yeah.
So what can we take away from here? That is, A, if we have objects, telegraph poles, bottles, whatever, of the same size and we put them in a line, then the further away they are, the smaller they seem to be. And the bottom of all the objects and the top of all the objects form lines that seem to come together in a vanishing point. And that vanishing point is usually on what we call the horizon. But there are more types of perspective. So you could have 2 vanishing points or even 3 vanishing points. But don't forget, the way we look at it at the moment is still the way you as an artist would have to look at it when you want to make a correct drawing. But with pictures from buildings in cities, etc., you will see exactly the same effect.
Slides from Myperspective Horizon Flat Earth video. that the parallel lines do not angle or converge towards the ground, nor do they angle towards the ceiling, nor to the left or right. They angle to the eye level of the observer. This image is a product of our eyes. These are horizontal parallel lines, yet we see them not as parallel, but on an angle towards a point in the distance. Now, of course, we know that they are parallel, but they visually are not. Here you can see parallel lines made up of bricks on the walls. The wall on the left, though, is headed out towards the horizon, and all the lines angle toward the eye level of the observer. The bottom ones angle up and the top ones angle down. Lines converge at a center point on the horizon called the vanishing point. Parallel lines above it angle down, the lines below angle up, the sides angle in. The vanishing point is the intersection of the horizontal and vertical axis of our eye position. It's parallel all the way out, parallel with the ground. The two, your eye level and the ground plane, are parallel all the way to the horizon, but it's the bottom ground plane that angles up to your eye level.
This is how we see the world, and any theories or notions about the shape of the earth must include this very simple law of perspective. The camera is on the table, it's a flat level surface, we have 5 lighters, all exactly the same height, but as we can see, they go off into the distance and appear to get shorter. Just a little bit of imagination can let you perceive what would happen to more and more lighters if I had more table to put them on. Okay, and so if we raise the camera up to the same level, now our eye level is level with the top of this lighter. You can see that all the lighters appear to be the same height.
The concept of perspective, eye level, and side or orthographic views, as Nathan likes to call them. This is a fence in a school car park or playground, and eye level is given here at the top of the fence. So I stood with my camera phone level with the top of the fence. A horizontal line across the screen shows us that eye level runs along the top of the fence almost perfectly. The playground is not entirely flat, so there's a little bit of deviation here, but not much. Here is a perspective line for the lower rail, and you'll see that this line will meet the horizontal line at some point far into the distance. The fence would have to continue for a considerable distance before those lines would meet. But of course it's impossible for the lower rail to ever appear in our view above the upper rail. Here, just for completeness, is the rail at the bottom of the fence. And once again, this line will eventually meet the horizontal line, the eye level line, some point very, very far into the distance. This is a drawing of the fence from side, or as Nathan likes to call it, orthographic view. This is a photograph of the fence from the side, or orthographic view. And here is the drawing of the fence, the cartoon, if you would like, Nathan, superimposed on the actual fence. You'll see that they match up perfectly. So side views do not include perspective.
But the moment we go down below that level, all the lighters appear to get shorter and shorter over distance, and they will also appear to get closer and closer together, even though the distance between them is about equal. this with looking down long corridors that appear to converge in the center of the observer's field of view. But at the same time, if we took a side-on view of what the observer is looking at, we know that the surface and the sky, or the floor and the ceiling in the corridor, never actually converge.
I have a first question to all of you. Do a quick answer based on your intuition, on your gut feel, on what your empirical evidence is telling you. Tell me, the little green lighter you see here, on which location does that fit best? Position 1, position 2, or where there is no lighter yet drawn, position 3 or position 4. Where do you think this lighter should belong? Just in your mind. Would be nice just to give a comment immediately before watching the rest of the video. The answer will follow later, but gut feel, empirical evidence, what do you see? What do you think it is? Give it now. Answer, answer. Don't measure, answer.
This is Jerry. His eyes can only see so far upwards and so far downwards. This is called his field of view. When Jerry looks at an object, the imaginary line between his eye and the object is called his line of sight. When Jerry looks across a level plane, anything remaining equal height across the ground, this is called his eye level. This is Jerry's house. On the door, there's a peephole. This peephole is at Jerry's eye level. And if you move the house across the plane to any distance, that peephole will always remain at his eye level. When Jerry looks at his house when it is close, it takes up a large portion of his field of view. That's called the object's angular size. If we move his house away, the house takes up less of his field of view, and its angular size is smaller. But the peephole remains at his eye level. But to Jerry, it looks like his house got bigger and smaller as it got closer and further away. But really the only thing that changed is its angular size, taking up more or less of his field of view.
Besides seeing it, we can actually calculate it. The angular size A is 2 times the arctangent of the actual size of the object divided by 2 times the distance to the viewer, which is actually the law of perspective, the mathematical law. Now I know not everybody is into math, and so far we did pretty good without math. But in cases you actually want to figure out how far something is away from you and you know how high it is, you can calculate it. Or if you're looking at windmills and in a windmill park in sea, for instance, you want to estimate or calculate how far the one windmill is compared to the other. You can actually do that when you understand the math. It is just a mathematical explanation of what we see with perspective. You don't need it, but you may use it to measure, define, figure out distances, sizes of objects, etc. So we ended with this angular size explanation, but forgot something else that Sly had already in his presentation as well, and as we can see here in the picture of Jan Vredeman de Vries, who did this first big study on perspective. The eye level. The guy in the back, his eyes are at the same level as the guy in the front, although his size is half of the guy in front. Apparently half. Let's have a look again.
On the door, there's a peephole. This peephole is at Jerry's eye level. And if you move the house across the plane to any distance, that peephole will always remain at his eye level. When Jerry looks at his house when it is close, it takes up a large portion of his field of view. That's called the object's angular size. If we move his house away, the house takes up less of his field of view, and its angular size is smaller. But the peephole remains at his eye level. But to Jerry, it looks like his house got bigger and smaller as it got closer and further away. But really, the only thing that changed is its angular size, taking up more or less of his field of view.
So if eye level is also a parallel line, then it goes parallel to the railway, to the road, and to the top of the telegraph poles, and will end up also in the vanishing point near the horizon. If the flat plane is big enough, eye level and horizon may be considered to be equal at the same height. But it must almost be infinite far away. So what does its eye level mean? That a person who is standing there has his eye level equally to or at the same level as the horizon, seemingly, and his head will stick out above, and his girlfriend, a little bit smaller, will be below that horizon. And if you now want to draw or make drawings and you want to project them further down the road, you have to take care that that remains the same. The eye level must remain at the horizon. The guy's head may stick out a little bit, and the girl's head must stay below the horizon, because that is the parallel line of your eye level. And this is very important. This is important, as our Jan Vredeman de Vries said. Everything below eye level you will be looking down to, and you will be looking up to everything above eye level, no matter how far away it is. So it is easier to imagine with this railway, which is below your feet. You will always be looking down on it. It may rise to eye level, but it will always stay below eye level, as do the telegraph poles that are higher than eye level will always stay up above the horizon and never go below it. They might end in a vanishing point, but even if you zoom in. So that is one of the other rules on perspective by Jan Vredeman de Vries. In this almost last chapter of this video, we are now going to look into the horizon, eye level in the middle of the frame. We have seen often that it is assumed that the horizon or eye level needs to be in the middle of the frame, which is probably the case if you can look very far away and you have a perfectly aligned horizontal camera. Then eye level, horizon may meet in the middle. But basically with horizon we mean something different. Horizon is best defined as the place where the air meets the water or the air meets the land, even if we do not see it. And that is very important to know, because the horizon is that point very far away where all the lines, parallel lines, would come together, the vanishing point. So another myth we have to address is that the floor rises to eye level, and the question is then, is eye level the same as horizon, or is horizon the same as eye level? Here the horizon is the floor at the end of this picture. So in this picture, eye level is actually the level at which the locks of the doors are. It is a parallel line to the floor all the way to the end. It's not where the floor ends that is the actual horizon or the eye level. The eye level remains the locks. What happens when we put a person at the end? We see it is higher. His eyes are higher than the locks. That is his eye level. So it is not the end of the hall, nor the end of the table where the vanishing point is, or where your eye level ends. The horizon is the end of this table. The horizon could be the end of the hallway's floor. But as I said before, eye level and horizon come together very far away. So why do they then say that the horizon is at eye level, and basically as shown here in another picture of Jan Vredeman de Vries, where it actually says horizon? That's because also this guy at the end of the hall, the horizon would be very far behind him at eye level, not here in this picture. And these people may walk and become smaller and smaller, so their angular size gets smaller and smaller, and at one point they are so small the artist or the architect making the drawing can't draw them anymore, and you may then assume they vanish into the horizon. But zooming in gives this, where all relational sizes are still the same as in the beginning. The telegraph poles didn't shrink. When you zoom in, they will appear again as high as they are in the beginning when we zoom out. And still the horizon will be far behind at eye level of the man.
The same height. In other words, if I'm at the same height as the person in front of me, right, and I point my camera towards the man's head's got to be in the middle of the camera, because that's where it is in my position.
And that's like on the rail track. No matter how far people walk away and how small they have become, the moment you zoom in, he will be at that same height again. So what about the sphere? Well, let's assume this is a picture taken on a sphere. A sphere that is flatter, much flatter than what I show you here. So, where in the first mile there will be a drop of 8 inches. Here we see a hole. The hole is probably 50 meters long, and already we see people in the end become very small. And in this 50 meters or 100 meters, it will have dropped like a few millimeters, a thousandth of a meter. Yet we see that the 100 meters here is enough to make the floor rise to what seems to be eye level. It is not really eye level because the people stick out above it. But you see the floor and they come very close, and this is after 100 meters. What about after 1,000 meters? Then we probably will no longer be able to see a good distinction between the person standing there. He will be so small, the angular size will be so small that he already, with the unaided eye, will seem to disappear in the vanishing point. So, as taught in arts class or drawing lessons, and as used by architects and artists, the laws of perspective, or the rules of perspective better, all comply on the flat plane and the sphere, because the sphere in the first 100, 200, 500 meters, the rise of the ground toward eye level, like in the hole, is happening. It is only after a mile that the horizon or the surface has dropped like 8 inches, and after 3 miles it will have dropped like 2 feet. By that time objects are so small we can no longer see it. Since we have cameras and zoom lenses, we now can see things happening differently than what the original lessons about perspective told us. But basically, for the first mile, everything on a flat plane or on a sphere with regard to perspective will be almost exactly the same, and the differences are so small you cannot detect it. For larger distances, no longer the unaided eye can assist you to make correct observations, and you will need cameras, zoom objectives, telescopes, whatever. It is important to understand that if the horizon and eye level are almost the same, if you can look far away enough, then tilt doesn't matter. So I can look a little bit down and then it seems that the horizon is higher, not in the center of the picture. I can look a little bit up and then the waterline seems to drop. But in both cases the horizon and eye level are almost the same, and it does not need to be in the middle of the frame. That is important to know. Eye level or horizon does not need to be in the middle of the frame. So another example of looking at tilt and how it does not affect the perspective is when we tilt the camera in this example. Some wooden clothes bags stand on the table. The last one is a little bit smaller than the others, and they have a certain relation to the edge of the concrete wall at the back. And nothing of that changes. You see the camera focus a little bit differently, but the relation, the size, nothing changes. It's only the height at which a horizon is that changes. So tilting the camera does not change the perspective. In this animation we can clearly see what happens when we start to pan. The total perspective changes, you know. The vanishing point suddenly is on the side and no longer where it was. The idea that the horizon should always be at the center frame will change. Suddenly it will be above it or below it. So panning is bad for perspective.
The moment we go down below that level, all the lighters appear to get shorter and shorter over distance, and they will also appear to get closer and closer together, even though the distance between them is about equal.
When people use grids, or when they claim certain things, lantern posts, power lines, whatever, are at the same distance, then you can use a simple trick to verify if it is correctly done. Perspective helps us to do this. I will now explain how you do that. We're going to test now whether this lighter is in the middle of those two. How do you do that? Well, you take the center of the first one, and then we draw a line to a point also approximately in the middle, maybe here. Yeah? And now we take a point here below and we move it up there to the similar point of the front one, and you see it basically crosses this in the middle, and that is the center. That's the middle of the distance between the two. That's a very nice test. So whenever you see a grid or whatever people show to show perspective, this is an easy test to check whether the lines in the vertical way and the horizontal way do match, and they have indeed the lines in the middle, because that is very important to understand. So we could do the same again, and we go there, and we go from there to there, and we already see there is some shift, so they are not entirely in the middle, but still it's pretty okay. That is important. This is a simple test you can always do. Question: what happens with the light post that is higher than eye level when I zoom in? It seems to move upward. You see? Upward out of the picture. So anything above eye level will move upward when we zoom in. So an eye object far away will seem to go up when we zoom in, and also more to the side. Actually, everything disappears from the vanishing point. What is higher than eye level will go up, lower than eye level will go down, left more to the left, right more to the right. Everything moves away from the vanishing point zooming. So it's not only that it gets smaller in height, it's also smaller in width. So the lighter gets smaller in total. And it is a big effect. And you won't notice it until I shift this one all the way here. Could you see, the funny thing now is that perspective makes this look smaller than that. Do you see that? And it is the same thing. You see? That is an illusion. It is important to know this illusion. But so the lighter did not only get smaller in height, also in width. So the appearance of its total size changed. See? But it also changes in the width. It gets smaller, seems to get smaller overall. But in the end, this one is exactly as big as this red one. Only it is a couple of centimeters further away. Do you see that? Amazing, isn't it? That is also what perspective does. And it even makes it now look smaller than that one. And that is how it fools your eyes. So another thing we learn is please take care. Do not trust your eyes. Your eyes are not a good objective way of looking at things. You can't say I have empirical evidence when you just saw it with your eyes. Look, it's the same size. I'm not changing anything. I'm just moving it. Try it yourself. So let's see. Suppose now I would make a block. Fill it. Now you would certainly think that this block, which is much higher than our little light here, should, when it moves to the side, cover up anything that's small. But this is not small. It is the lighter, which is equally big as our red one. And it will stick out. Because anything that is, how do you say it? Smaller, lower than eye level, will always stay lower than eye level. And anything bigger than eye level will stay above eye level. Remember the animation of Phuket where he had this little sun moving in parallel over the top of the bottles. Basically here you can imagine the silver caps of the lighters to be, let's say, the sun, and how much that distance does to its size. Do you see that? And it is here not by far, you know, somewhere there was the horizon and the eye level, and this is already what change in size we see with lantern posts, lights in the sky, whatever. So here equal size, and then it is shrinks so much, it becomes so small.